Hello, everybody, and welcome to our first of many, many, many discussions of things that rotate. So, here we have this kind of weird shaped object, right? And we're going to let it rotate. Now, up till now, we really haven't dealt with rotation. Right? We've dealt with things mostly, really, even if we haven't said this, we've dealt with them kind of like they're particles. Like all parts of them move the same. And we can pretty much get away with that with what we've done up to this point. I mean, even if we took like a cart that we had on a track, sure, the wheels move differently than the mass of the cart, but the wheels were kind of small, and so we could ignore them, and it didn't really seem to throw anything off. Right? So we just dealt with it as if it was a block all moving together. Right? But that isn't true when something rotates. Right? Things change when things rotate. So what we have to start out with here is by trying to figure out how we can define some of the quantities that we've talked about before for linear terms, right, so that we can build similar kind of rotational models. So let's take a look at this thing, right? I could put this thing into rotation. If you notice, it's rotating about that point, right? And that point is what we call an axis of rotation. No big deal. A lot of new terminology because things are rotating, so you got to keep track of all the verbiage here. Okay, so that's the axis of rotation. Well, if I want to try to figure out again how to describe where this object is, maybe I could do that by picking a point. Maybe that would help. So here's a point, right, of this object. If it's rotating, do you notice what that point's doing? It's moving in a particular shape, isn't it? Watch it again. Yeah, right? It's moving in a circle. And of course, we know a lot about circles. Very first day of class, we learned that the circumference of that circle, the distance around it, right, is pi times the diameter, or 2 pi times the radius of that circle. And so that's a little fact that we know about this circle that this thing's moving in that might come into play at some point in this unit, or many points in this unit. But still, how do we describe where that point is? Well, we could draw a line from the axis of rotation to that point. This is what is known as a reference line. And perhaps we could describe that reference line, and that's how we could define the position. So if we put this thing in motion, you notice that the reference line rotates right along with that point, right? So let's consider this at just some random place. It's over here. This is where it is. How could I tell you where this was without drawing a picture? Well, if I want to define where A is, there's a couple things I could look at. One is I could draw in that reference line. But notice, what is this reference line to this circle, right, that the point moves in? Yeah, it's the radius of that circle, right? And radius denoted by a lowercase r, sometimes a capital R. It's just going to kind of depend, but I'm going to use a lowercase r for the purposes of right now. But that's not enough, right? If I just said, well, the object has a radius, or a point on the object has a radius of this, that doesn't really tell us where that reference line is, just tells us how long that reference line is. But there is something else that we could use here. Right? What if we found that distance? Right? If we call this 0, the positive horizontal, like we've done with angles and things, right? And we measure that and we describe that, could we then fix this position? Sure, right? If I said, here's this object, here's its axis of rotation, right now, a point on that object has a radius of this, and it's this far away from 0, right? You could place that. Well, you might know what this is called. Right? This is called an arc length. Right? Arc length. It's denoted by the symbol s, lowercase s for arc length. I don't know why, but it is. All right, lowercase s for arc length. A is already something else. I don't know. Right? So with the radius and the arc length, we could figure out where that point is. Right? We could place that point in its rotation. Of course, as it rotates, right, the radius might not change for this point, but certainly the arc length would change, right, as it rotated. But what if it was a different point? What if we had this point out here? Here's point A. What if it was this point? Well, this point, the object's still in the same place it was before, right? That hasn't changed. The orientation of this object hasn't changed. But notice, if we looked at this point instead of this one, there's if that's the radius and the arc length at point A, this is the radius, and this is the arc length at this point. Well, that radius and that arc length represent the same position as this radius and this arc length. It's the same orientation for the object. But they're different values. So this kind of begs the question here. If we pick this other point and the radius changes by some factor, by what factor does the arc length change to give us the same position? Is there a pattern? He asks. Right? And so that's why our first lab in rotation is going to be to find graphical and then mathematical representations of the relationship between the arc length and the radius for a particular reference line. So basically, we're going to take a single reference line, and we're going to pick a bunch of points along that reference line. Right? We're going to measure the radius to that point and the arc length to that point, and then we're going to make a graph and see if there's a relationship. Right? Is there some way that we can, something special about that relationship that we can use? Okay. Now, to me, it would be kind of boring to just do one. So when you get into the back and you work on this equipment, you're going to see a set of 6 circular objects back there. They're cake rounds that we used back on the very first day of physics. Right? We used to find the circumference lab. And these objects on one side of them, they were just cardboard. On the other side, though, they have 3 reference lines drawn. A, B, and C. Okay? But, of course, they're different size circles. Okay? So, basically, if you take a look at the lab sheet, okay, you have 3 data tables, 1 for reference line A, 1 for reference line B, and 1 for reference line C. Okay? And you are going to measure the radius and the arc length for reference line A on all 6 circles. Now, if you line them up, you'll notice they match, right? They're the same reference line, right? So it's kind of like this picture, right? But there's 2 different circles, right, that I've used for these. Okay, so it's pretty similar. You'll see what I mean when you get there. But I decided to put 3 different reference lines in. So you've got to measure all the radii and arc lengths for A on the 6 circles. You've got to measure the 3 radii and arc lengths for B and the 3 radii and arc lengths for C. Remember that 0 arc length is over here at the positive horizontal. So if you're measuring C, you've got to measure this distance all the way around to there. By the way, please don't calculate anything. Measure. Right? Like in the circle lab. Measure, measure, measure. Right? Arc lengths around, right? And radii. All you need. You'll note that I want everything in meters. When you get done, I want you to make a single graph that has all 3 relationships shown. All 3 data tables on one graph. Okay? That's because I want you to be able to compare the relationship between the arc length and the radius for A, B, and C. Okay? It's very important in this lab. So on the lab sheet, I have included some steps of how to create enough columns in your data table inside of graphical analysis. Right? So you can have radius, and then you can have A, B, and arc length A, arc length B, and arc length C. Right? And then how to set up the single graph so that you can see all 3 on one set of axes. If you're having trouble at that point, call me over and we can look at it. Eventually, when you get those 3 graphed and you've done your linear fits on them, there is a place, there's a Google form on the schedule doc that you can put in the slopes that you got, right, for reference line A, reference line B, and reference line C. And then we're going to discuss this and build this idea of position of a rotating object.